All right.
ahead.
Thank you. Yeah, I'm Phillip. I'm from the HPI in Potsdam, Germany, and I created Actix-Telepathy, which, as already introduced, is an extension to the Actix actor model library, so that you can have remote actors and build distributed systems in the actor model itself. So my actual research is something completely different. I'm a researcher in anomaly detection on time series, and last year we created with other people of my chair a large evaluation where we used about 150 algorithms. So we implemented these and tested them on a lot of benchmarks, around 1,000 data sets. And we found out that many of these algorithms are either qualitatively bad or they have lots of timeout and out of memory errors when the data sets grow large. And therefore we thought to ourselves, we need a technology if we want to also build algorithms in this case that has certain requirements and is able to analyze all these big data sets. And the three requirements that we had were they should be resource efficient, because we don't want these errors to happen for our algorithms as well. Reactive, obviously, that's why I'm here in this workshop, so that they can adapt to the data and the different distributed parts can talk to each other. And it also should fit in the Python environment, because most of these algorithms are written in Python. The benchmark setups, benchmark libraries are also Python, and so we wanted it to be integrated. And one language that popped up that was suitable for us was the Rust language. It's memory efficient, quite fast in comparison to Python, and it's also easy to integrate into Python. So you can port it to, so you can create Python libraries out of Rust binaries and frameworks. And the problem was that the actor model libraries don't have these remoting features. I think I don't have to explain what the actor model is in this context, so I will just skip over these slides and jump right to this one here. So these are the current or the largest in terms of downloads actor model libraries that we found for Rust. The biggest one, this logarithmic here, the y-axis, the largest one is Actix, with at the moment, these numbers are from this week, almost 6 million downloads, and then the second largest is 110,000 downloads, and then it gets lower, yeah. And so we said, okay, let's go with the Actix library. None of these libraries support a remoting feature, so they all run local. Let's go with the Actix library. So now I'm going to introduce you how you can build some very small basic applications in Actix itself. So it all starts with importing the Actix library itself. Then you create, in this example, an actor that has a state which is a positive integer number called myActor, and you implement an actor trait for this actor so that it acts as an actor and can receive messages. Each actor has a started method, which is called once the actor has started. So in this case, this actor, if it once it starts, prints out that it has started. My actor started here in green. Then you would create a message. In this case, it's called my message, and has some these yellow lines above it are macros. So the first one will implement a message trait for this struct, and the second one defines what the return type is. But in all these examples, there are no return types. That's why they are empty. And then you would implement a handler for this message for the already created actor, where you would also define the result, which is empty, and the actual function that is called once the message arrives. That's the handle function. In that case, the actor would print out that it has received this message, but also this the position where it would update its state based on the messages that arrive. And you start the application by creating this actor, starting the actor. You receive the actor address, and then to this address you can send messages. And in the end we have a sleeping function so that we can wait until the message arrives. Right, so once you start the application, it will print out that the actor has started, and then the system sending a message to it, and the next printout line would be the message is received. So the structure of this application looks like this. There's a message, an actor receiving a message from the system, basically. Then, in the second example, we will create a second actor, which we call my second actor. And as a attribute, it has the address of another actor that can receive my message. This actor will then print out that it has started. Once it starts, sends a message to the address it has as an attribute, and tells the user that the message has been sent. Starting the application would look like this. You start my actor, you receive the address, and then you add the address to the second actor, start this actor, and wait for 3 seconds so that everything finishes. The output of this application would then, as expected, be similar to the other one, where you have an actor that starts and receives a message now from the second actor that knows its address. But now the question arises: so if we have now the setup that one actor should be on a different computer than the other actor, we would like to have a remoting feature, and that is not supported by Actix. That's why we created this with the telepathy extension. And an example would then look like this. The goal of this library was that it should be easy to switch from one library from the base Actix to our extension. And so the only thing you have to do in theory is that's the same code as the one before, but now we have these two macros, these yellow lines above my actor, where we are defining my actor to be a remote actor, and define the messages that are received over the network, so remote messages. And the remote message then, we replace the macros of the Actix library with remote message, and also it has to be serialized and deserializable. And now the actor is able to receive this my message over the network, and the message handler stays the same. So this would be then easy to implement if you already know the Actix library. And now the problem is, once you start the application, you don't have the remote address of the other actor on the other computer. That's why we cannot tell the second actor from the beginning that this is its recipient here, the address. So we have to find a way around this. And this is happening by listening to cluster events. So there's a trait called cluster listener, which we will implement for the second actor, and a handler that's listening to cluster logs. This is an internal behavior of the telepathy application. So you can, any actor can subscribe itself to listen to cluster events. In that case, once a cluster node joins the cluster, an event log is sent to in this case my second actor, which can either be a log saying there's a new member, as we see here, or a member has left, which in that case doesn't do anything. But in the first case, the new member has arrived. We get the node that arrived with a attributes like the IP address and some utility functions like get remote address. So in that case, in this line, the my second actor would receive the remote address of the my actor on the newly joined cluster node, and can then send the same way as in the usual Actix behavior a message to this remote address. So this would then be the main function that would start everything. We start my second actor, we start my actor, and then we start a new cluster. Give it the own address where it's listening to incoming requests, and some seed nodes so it can connect to other nodes in the network. The application would then do something like this. We have so basically we have both actors on both systems, and once the cluster connects both nodes together, the my second actor receives the remote address from the my actor from the other system, and then will send the message. And I hope I can just jump out of here to show you the like a very small demo. Yeah. So we have one node on the left here. And we have another node on the other side. The left node starts on the port 1992. The other one on the port 1993, and the right one takes 1992 as a seed node, so it knows where to connect. And when we start the left one, it says that its actors has started and it's not doing anything. And then once we start the right one, it says, okay, my message is received. So it connected and then got the address from the other node and sent a message. And that one also received a message because they do basically the same. Right, let's jump back in. The architecture of the Actix-Telepathy library looks like this. We have a cluster node, a cluster actor. These are system actors. A cluster actor and a gossip actor. And the gossip actor is sending the new members that are joining the network, the addresses of all the other members that are already joined in the cluster. Network interfaces are created once a new member joins in the cluster. So for each member, each system has a network interface to the other members. And then there's also this address resolver, which is handling the forwarding of incoming messages to the right actor on the local system. Then we have a remote actor trait, as I've already shown in the derive macro, and a remote address. These are these new kind of objects that are floating around in the telepathy system. And once you send a message from one actor to the other, the dashed line shows that it knows the address. So the actor on the bottom right will internally send a message to its network interface connected to the network interface of the other machine. This one sends this message to the address resolver with the recipient name, and the address resolver then knows where to forward this message to the actual recipient. This all happens in the background, so the user does not have to know this kind of behavior, as I've shown in the examples. And this all happens when you say this function on the lower left, do send this message. We did some benchmarking experiments here, compared it with Akka and Orléans, since these are like the big actor models from other programming languages. And in this example, we had a distributed application that is searching for prime numbers in a range 0 to 100 million. and the x-axis shows the distribution. So how many nodes participated in this cluster. So here's 100. No, right, yeah. And the y-axis is milliseconds. And as you can see, Actix-Telepathy scales in a similar way to Akka and Orléans. And since Akka is running on the virtual machine, we also ran two different versions with restricted memory. So we measured the memory used by Actix-Telepathy and then restricted the Akka system to this amount of memory, and then it only goes until 10 nodes, and then it stops because it runs out of memory, also with extra buffer. In another experiment, which we call power ping pong, are two nodes that are sending messages back and forth, and with each sending, it doubles the size of the message to see that in this case, we want to show that the serialization and all this message forwarding does not affect the performance in a negative way. And here we also see that it's right in between Akka and Orléans. And in the last experiment, we actually had this use case from the beginning. So we wanted to actually use it for building a distributed time series anomaly detection algorithm. And one particular algorithm that is finding anomalies in time series called series to graph. What this one is doing, just briefly, it looks at the time series, spins it around a geometric origin, and then builds a graph out of this geometric representation. And out of this graph, it can read which parts of the time series are anomalous and which are not. And a master student of ours distributed this algorithm in Akka. In our experiment, we then implemented it in Actix-Telepathy, and then could nicely compare it here. And as we can see, Actix-Telepathy actually scales very well with the number of nodes. Up to 120, and Akka from let's say around 60 nodes has a larger communication overhead, and so the runtime increases then again until it stops because it doesn't communicate anymore if you have too many nodes in the network. Right. And so we actually then extended this algorithm even further to run it on larger data sets, and it's at the moment under review at the ICDE. So let's see what comes out of this. Right, and that's basically my story using the actor model libraries. This whole project is open source. You can find it on the left QR code. This is my university website. And with that, I'm open to questions. Thank you.
Thank you very much. Are there any questions? Because I have one first. What happened to Erlang?
You mean in terms of benchmarking?
In terms of benchmarking?
Yeah, we didn't use it.
Any particular reason, or just because
so we
had to make a selection?
Yeah, so one reason why we didn't use it is the problem with all these anomaly detection algorithm libraries is they use some like stuff where you need other libraries doing data science and this and that, right? And so with it was already quite hard to build an application like this with Java, I have to say, and Orléans. So yeah.
So it's about the remaining ecosystem.
Exactly. Yeah, we wouldn't use it. Yeah.
Questions.
Okay, thanks for the nice talk. I'm just curious about this architecture diagram. So how do you manage the remote references? Do you do some kind of distributed garbage collection or something?
Sorry.
Distributed garbage collection was.
The garbage collection is done by Rust, and so the internal structures, there are open TCP channels between these network interfaces, And so this is then also handling the heartbeats and everything that's internal. So we didn't have to implement this. And right, yeah. But the garbage collection is done by Rust and.
No, yeah, I'm just. Yeah, my question is about remote references. So remote reference should be kept when the how to say the target object is arriving. No? So that,
okay. So the remote references are implemented the following. No. I hope you can still hear me. These network interfaces exist for each connected node. So when you have one machine and this is connected to 3 other machines, then this one machine has 3 network interfaces. And so if it wants to send a message to one of these 3 machines, it goes over this network interface that is connected to this machine that has an open TCP channel, and in this message is wrapped in an object that holds the message, the serialized message itself, and an actor ID, which the actor ID is like this local address, and this is translated by the address resolver. So the network interface receives a message, unpacks it, deserializes the message itself, looks at the actor ID, and then the address resolver is forwarding it based on the actor ID.
Okay, thank you.
So do you allow actor references to be passed as arguments of messages to other actor references?
Yes, but they don't work. so you can okay. That was the question.
The garbage collector.
Yeah. No.
You have a spaghetti of references.
Exactly. No, that doesn't work. So because the local addresses are basically addresses on the memory saying this actor. But this doesn't work remotely here.
I have a slightly related question, which is about the ownership type system and what interaction it has with the actor model. Like, is this a positive interaction? Do you not notice any insights?
The Rust ownership, you mean? There are some problems. So I said that I don't use the message response, right? So the message response was always empty. The problem here was that if you wanted to have a message response, then the ownership and the whole Actix structure doesn't really allow it. So you would need to hack your way around, and that was too ugly. So I said no, I want to have the clean implementation distributed, and then.
So you would say the ownership type system is not, let's say not at least not now well compatible with the actor model, at least not in the remoting case.
Not in that particular case that I encountered, but.
And does the remoting make it worse than local Actix, or is it already a problem in just Actix?
So I encountered this problem only in the response. In this remote response feature that I didn't implement in the end, but in the rest it's fine because it's super isolated, since you are working with these handlers and they're very isolated functions which do not access other features. Yeah.
Further questions from the audience? Because I do have one last one,
yep.
Which is related to your last point. So you added basically new API surface for some remoting features, like getting remote references from the nodes. Did you have to adapt anything at all from the just actor API surface, or does what Actix has work just fine even for the remote case?
Yeah, I didn't change Actix. Yeah, it's 2 libraries you implement. They have to.
So basically, I guess what I'm saying is the programming model remains exactly the same.
Yes.
For the remote case.
Yeah. That was the goal of the. Yeah.
Maybe one final. Maybe you mentioned it. I don't know. So what happens if an actor explodes? You have a heartbeat.
Yeah.
Do the other ones get notified? Do they have to clean up their reference tables and stuff like that? An
exception happens. Right,
and then
there are some structures in Actix around this. So you can have actors that are watching different actors, and once these actors fail, they can be restarted. They get notified, but this is already implemented in Actix itself.
So that's like spawn link in
Right, and so if the TCP channel somehow disconnects, then the network interface fails, and then the cluster is notified. Yeah.
Great. I guess then let's thank the speaker again.
Thank you.